Hello everyone. In this video, we'll discuss the occurrence and extraction of metals. Now, where do we get metals from? The primary source of metals on Earth is the Earth's crust. Earth's crust is all the rock, all the soil, the land that we see, and even under the ocean, the floor of the ocean, it's all the Earth's crust. But most of the minerals we can get on land, so we usually consider only the land part. Okay? So we have minerals of almost all metals on the Earth's crust. We also have seawater, which is a very important resource. It has minerals of sodium, magnesium, and several other alkali metals. Even lithium for that matter. But most of our discussions will relate to minerals in the Earth's crust. Now I say minerals. What is a mineral? A mineral is a compound containing the metal of interest in an extractable form. So basically, any compound of any metal that you can find is called a mineral. Okay? But it is not always easy to extract the metal from a mineral. It is possible, but it is not easy. An ore is a mineral from which the metal can be extracted economically. What that means is if you have an ore and you manage to extract the metal from it, you can actually make profit in doing so. It is still viable to extract your metal from an ore. Whereas a mineral, it may or may not be viable. You might not have enough concentration of it. It might require very advanced, difficult chemical processes. It can be done, but it is difficult. An ore, it is easy. So how do you extract metals? Let's go back and visit the reactivity series. Now, if you remember, we said that potassium, sodium, calcium, magnesium, and aluminium were highly reactive. And then we said that zinc, iron, lead, copper were of intermediate reactivity, and then silver, gold were of very low reactivity. So we can say that these are highly reactive metals. These are intermediate, and these are low reactive. Okay? So what we can do is, for a highly reactive metal, it becomes difficult to use any kind of displacement reaction. So what we do is we get this out using electricity. So electrolytic extraction. Okay? Now the metals of intermediate reactivity, they can be reduced by heat or carbon or both. So these are done using thermal carbon reduction. Okay? The metals that are low reactive, that don't react very well, they are usually found as it is. So usually found in native state. By native state, I mean silver will be found as silver, gold will be found as gold. Copper, on the other hand, will be found as an oxide, as the ore malachite, or as a sulfide, pyrites. But it is not native. Whereas potassium, sodium, calcium, these are found as oxides or chlorides or things like that, which are very difficult to displace. Okay, so based on where your metal is, you can adopt a different kind of strategy to extract it. Now there is a general step-by-step procedure that we use when we speak about extraction of metals. So first we take the ore. Now we know what the ore is. The ore is a mineral from which we can economically extract a metal. So what can we do with the ore? We have to concentrate it, right? Now I will write in different colors so that you understand what I'm talking about. Concentration of ore. Now concentration means increasing the quantity, increasing the amount of metal present in the ore. Now ores are found by mining, right? And during mining, a lot of other unnecessary substances are there. For example, there could be sand, there could be some other mineral that you don't want. So all these come in and they reduce how much ore is available for extraction. After you do that, you decide what kind of material you're talking about. So if it is highly reactive metal, you have to adopt a different strategy. If it is a medium reactive metal, that's a different strategy. Like I said, you would have to use carbon. If it is low reactivity, that is a completely different strategy altogether. Now we said that metals with low reactivity are usually found in their native state, right? Some of them are also found as sulfide ores. Sulfide is an ore with sulfur, so sulfide ore or native. If it is a sulfide ore, all you have to do is you have to roast it. Roasting is a process of heating in the presence of air or oxygen. So when you blow oxygen into your furnace and then you heat it, that process is called roasting. So by roasting a sulfide ore, you remove sulfur in the form of oxides of sulfur, SO2, SO3, and the metal remains. So you directly get the metal. And this metal you can then refine, and then you will be able to get your material of quantity. Okay, so if you notice, I am writing the steps in orange and I'm writing the materials in blue. Okay, so if you follow, a low reactive metal is either a sulfide ore or native. If it is a sulfide ore, you roast it. By roasting you get the metal. Once you get the metal, you can refine it and you can keep it as it is. Okay, now what about if my material is of medium reactivity? If it is medium reactivity, it could be of two forms. It could be either a sulfide ore again, or it could be a carbonate ore. Alright, a carbonate ore is iron carbonate, siderite, and a sulfide ore could be iron pyrites or copper pyrites. Now sulfide ores, like I said, you will process them with roasting. Roasting, as I said, is heating in air. Okay, but what about a carbonate ore? A carbonate ore is already containing oxygen. So all you need to do is heat it in the absence of oxygen. If you do that, the carbonate decomposes to give you an oxide ore. And this kind of heating without air or oxygen is called calcination. So once you calcine an ore or you roast a sulfide ore, you will get an oxide, a metal oxide. Okay, let me write this again. You will get a metal oxide. Now once you get the metal oxide, you can decide what method you want to reduce it. You can use carbon or you can use a displacement reaction. Now carbon is also a kind of displacement reaction. I'll give you the exact reactions in a bit. You have to do reduction reaction, and once you get that, you have to do purification of the metal. Purification of the metal. And then you get the metal that you desire. Okay? So let me just map this out for you. A medium reactive metal can be found in the earth in the form of either a sulfide ore or a carbonate ore. A carbonate ore is heated in the absence of air, which is called calcination, and a sulfide ore is heated in the presence of air or oxygen, which is called roasting. Now both these processes give you a metal oxide, and a metal oxide you can choose how to reduce. You could either use a displacement reaction or reduction by carbon, and then you can purify it to get the metal you desire. Now metals of high reactivity, we really can't do anything with them, right? So we just take the ore and we electrolyze it. Electrolysis of ore. Once you directly electrolyze it, you get a metal, and this metal is pure. So you directly get a pure metal. Okay? This is very straightforward. A highly reactive metal, you electrolyze it, and then you get the pure metal from it. So now these are the steps that you have to perform if you have to get a pure metal. Okay? Now each of these steps I will explain in detail. First and foremost, we speak about enrichment of the ore. What is enrichment? Now ore that we mine from the earth have a large number of impurities like soil, sand, dirt, other minerals, which are called gangue. Okay? Gangue, that's how you write them. You have to remove these impurities from the ore before you can extract the metal. Okay? Now, there are differences between ore and gangue. Now these differences could be physical or could be chemical. Now if the differences are physical, you can use various techniques like magnetic separation or centrifugal or even air blowing. So this happens when you have one material that is very dense, say the ore of tungsten or iron, and then the waste material is basically sand or something that's very light. Now chemical processes are a little more complicated, they're a little more involved, where you use a certain reagent to cause the gangue to react and come out as a slag. Okay? So you can separate all these things from your ore using either a physical or a chemical process. Now that you have your enriched ore, it's time to see how you can extract your metal. So low activity metals, how do you extract them? Like I said, mercury is a low activity metal, and mercury is extracted directly by roasting. Okay, so when you heat a mercury, these are sometimes the sulfide ores, and when you heat them in the presence of air, the sulfur is driven out and you can get your metal. So the ore that we are speaking about is cinnabar. Cinnabar is an ore of mercury. It is mercury sulfide. Okay, when you heat this in air, you get mercury oxide, HgO, and when you heat this further, you will get mercury metal. Okay, so how do you write this chemically? You have Hgs plus O2 gives HgO plus SO2. All right, now let's balance this. We require okay, we have 3 oxygens. That means we get 2 of this, 2 of this, and 2 of that. Okay, so this is upon heating. Now, when you heat mercury sulfide in the presence of air, so this heating is actually roasting. Okay? So by roasting mercury sulfide in air, we get mercury oxide and sulfur dioxide. Now, sulfur dioxide is a gas and that will escape. Okay? Now, mercury oxide, HgO, when you heat it, you will get Hg, which is a liquid, mercury is a liquid, remember, plus oxygen. Okay? So that's all. It's a very simple process. You don't have any complicated steps over here. You can directly roast the ore and with that heat extract your metal directly. The same thing happens for copper, and copper is usually found as Cu2S, copper sulfide. Okay? Copper sulfide can be reduced to copper by heating in air, and this is again roasting. Okay? So let's consider Cu2S plus O2 gives Cu2O plus SO2, and SO2 is a gas that will escape. So to balance this, it's pretty much the same. We require 2 of this and 2 SO2. All right. So what happens then? The continued heating will cause Cu2O to react with Cu2S again, which is still present, and that heat will cause Cu plus SO2. All right. So let's just balance this. Yeah, that should be it. So sulfur dioxide is released as a gas and you can directly get copper. Okay. The same way you directly get mercury. Now, these are materials that are very low in the reactivity series. What about metals that are of medium reactivity? So metals of medium or intermediate reactivity. What about them? So these are like Fe, Zn, Pb, etc. Okay. So let's consider zinc. Like I said, let's go back to our table. If it is a sulfide ore, you want to roast it. If it is a carbonate ore, you want to calcine it. Okay. So what if we have zinc sulfide? ZnS plus O2 gives ZnO plus SO2, and SO2 is a gas. So again, this is exactly the same balancing we did before upon heating. And now we have a metal oxide. Let me just mark this. This is zinc oxide. Now what if we have a carbonate ore? Let's say ZnCO3. If it is a carbonate ore, you have to calcine it. Okay, heat. This is roasting. This is calcination, because there is no air, there is no oxygen. Here we have oxygen, here there's no oxygen. So when you calcine it, you get ZnO plus CO2. CO2 is a gas which can escape. So this is again zinc oxide. So irrespective of whether you have a sulfide ore or a carbonate ore, you convert it into zinc oxide. Now that you have zinc oxide, what is the next step? What can you do? You can take the zinc oxide, mix it with carbon in its solid form, which is usually coke, and then you heat that. By heating that, you will get zinc metal and carbon monoxide gas. Okay. Now this step is a reduction reaction. So let me just write that. This is reduction. And this is your zinc metal that you've been looking for. So what is special in this reaction? Carbon is displacing zinc from zinc oxide to give you zinc and carbon monoxide. Okay, it is a displacement reaction. Now you need not displace only with carbon. You can use any metal that is higher in the reactivity series. For example, let's speak about extraction of manganese. So manganese is available in its oxide form, MnO2, Mn plus 4. Now manganese, you have issues extracting with carbon because it can form some other compounds and it is a mess. So how do you do it? You can use a displacement reaction, and aluminium is one of the highly reactive metals, if you remember. So you mix it with an aluminium powder and you heat it to give you manganese and aluminium oxide. Okay, but please note, this is an exothermic reaction. You just have to ignite it, you have to spark it, and then it will burn. Okay, so we require alright, let's just balance this. Okay, so this manganese that you get is the metal that you're looking for. Okay, now this reaction, you are using aluminium to displace manganese. Aluminium displaces manganese and forms aluminium oxide. Manganese comes out straight. So this is a displacement reaction, and this specific reaction where you use aluminium powder to extract a metal is called a thermite reaction. Okay, thermite reactions are very important because it is used in joining of railway tracks. Now link 1 in the description gives you an example of thermite reaction. Alright, it is also called the aluminothermic process, and the reaction that they discuss in that video is the reaction with iron. So you have Fe2O3 plus 2Al gives Al2O3 plus 2Fe. Now this is the same reaction that is used in fixing railway tracks. Okay, this is the aluminothermic process or the thermite reaction. Now what about metals at the top of the activity series? Highly reactive metals. How do you extract a highly reactive metal? A highly reactive metal, you have to perform electrolysis. Now if you remember sodium chloride, we performed electrolysis of the solution to get sodium hydroxide, but that it was in water. So to extract a highly reactive metal, we must electrolyze molten salt. Okay, what is meant by a molten salt? A molten salt is a salt that has melted. Okay, it is in liquid state, but it is not a solution. At high temperatures, salts melt, and these melted salts can conduct electricity, so you can cause electrolysis to happen. Okay, it is very simple then. So NaCl, when it is melted, you get Na plus Cl minus, but there is no aqua, there is no water medium over here. So at the cathode, which is the negative electrode, you have Na plus electron giving you Na metal. Okay, and at the anode, which is the positive electrode, you have chloride ions that give away the electrons and form chlorine gas. Okay, so that's it. It's a very simple process. You can extract even aluminium. Aluminium is also extracted using electrolysis. Okay, now we have extracted our metals. It could be low, medium or high reactivity. But once we extract the metals, they are still very impure. Okay, so metals extracted must be refined to remove impurities and to obtain pure metals. Okay, the simplest way to refine a metal is again by using electrolysis. Only over here, both your anode and the cathode are made of the same material. So let me draw this out for you. Consider a large electrolytic tank in which we have two electrodes made of the same material. Okay, let's consider copper. And both the anode and the cathode are made of copper. Okay, and this is connected to an external circuit with a switch. The positive side, which is the anode here, and the negative side, which is the cathode here. Please note the anode and cathode for this and that reaction are slightly different. But the reason for that you will understand later. I don't want to confuse you right now. So this is in a solution of copper sulfate, CuSO4. And both these electrodes are copper. Okay. Now when you pass current, what happens? The copper from the anode, it releases electrons and goes out as Cu2 plus. And Cu2 plus from CuSO4 pick up the electrons and go in and sit on the cathode. So over time, the size of the anode keeps reducing, and over time, the size of the cathode keeps increasing, right? Until the reaction is completely over, where the anode is completely consumed. Now in this process, a lot of dirt is collected at the bottom of the anode, and this material is called anode sludge, anode mud or anode sludge. Let me spell that again for you. Anode sludge. Okay, and the solution, the electrolyte we have is acidified CuSO4. Okay, it's a pretty simple process. By doing this, you can get a pure metal. Now this side is pure, this is pure copper, this is impure copper. Okay, all those impurities come off the electrode and are deposited as anode mudgers, anode sludge. Okay, all right. Now we've spoken about how we've extracted the metals. The last part of this lesson speaks about corrosion, how we lose the metals that we've extracted. Okay, so corrosion, like I've described before, is the process in which the surface of a metal wears out. Okay, silver becomes black, tarnishing. Copper becomes okay, so let me just write Ag reacts with sulfur in the air in the form of sulfur oxides to form Ag2S, silver sulfide, which is black. Okay, so silver tarnish is that black color that you see on silver articles. Copper reacts with CO2 to form copper carbonate, to form a carbonate which is green. Now copper is red in color, but if you keep copper outside for a long time, it develops that green coat. Okay, iron, when exposed to humid air, reacts to form Fe3O4, which is rust. Okay, it's a brown flaky substance. Iron rusts when there is both moisture. Iron rusts when there is both oxygen and moisture. So you require both of that for it to rust. Okay. How do you prevent corrosion? Now, corrosion is a serious problem. Even in the industry, in cars, in day-to-day life, you don't want anything to rust because rust is waste of the material. It is degradation of the material. Okay. So how do you prevent corrosion? You prevent corrosion by painting. If you paint the surface, then there is no oxygen coming in contact with your metal, so the reaction won't happen. The next one is oiling or greasing. Again, when you apply oil or grease on a metal, its contact with air is blocked off, and when that happens, oxidation cannot happen, so that is fine. The third one is galvanizing. Okay? Galvanization. Now, galvanization is the process of protecting an iron article by electroplating it with zinc. Okay? It's not necessarily electroplating, it could be any form of coating. By coating it with zinc. A thin layer of zinc is coated on top. Okay? If the zinc is broken, it starts rusting again. So you have to keep it safe by preventing that zinc from breaking. The other method of preventing corrosion is by alloying. Okay? Now, alloying is the process of mixing small quantities of other metals to improve corrosion resistance. Okay, it also has other properties, but fine. What you have to understand is when you alloy a material, the properties change. Okay, so for example, we know iron can rust, but when you mix iron with a small amount of nickel and chromium, we get stainless steel, right? Fe plus Ni plus Cr will give you stainless steel, and this does not rust. Okay, but stainless steel also doesn't have the same properties as iron. It is not as electrically conductive, and there are other problems with it. So alloys are not always the answer. That's what I'm trying to tell you. So how do you make an alloy? You make an alloy by heating the metal, melting it. You melt iron and then dissolve the other elements that you want to form the alloy with. Say melt. And by dissolving this and then cooling, we get the alloy. Okay, that's the process. It has to be in proper proportion. Alright. Now, just a side note, just something you should know. If one of the metals in the alloy is mercury, then the alloy is called an amalgam. So an amalgam is an alloy of mercury. Okay. Another note, the electrical conductivity and the melting point of the alloys are usually lower than pure metal. Okay. So we know that copper is an excellent conductor of electricity, but brass, which is copper plus zinc, and bronze, which is copper plus tin, are not as good as copper when it comes to electrical conduction. The same way, solder, which is an alloy of tin and lead, has a very low melting point, so it is very easy to melt it. That is used in joining electrical wires together as solder. So solder is Sn plus Pb, easy to melt. Okay, it is used to join wires together. The process is called soldering. All right. So alloys are not as good as the pure metal when it comes to conductivity, but they also have a lower melting point, so they have certain applications. Okay. So with this, we are done with how you can extract metals, how you can purify the metals, what happens when metals corrode, and how do you prevent metals from corroding. Okay. So this is the end of this chapter. Thank you very much.